Brent.
I'm Adam.
And welcome aboard. So what have we got today, Adam?
Well, we have a really special episode today. We actually have a special guest with us from DPL Labs. We got Jeff Boccaccio.
When you say special, do you mean like the short bus special?
I didn't say that. So, we have Jeff Boccaccio with us today from DPL Labs, and we're very excited to have him here. As always, I apologize for the audio right now at this point, everybody. We're actually using our overhead camera to pick up the audio because as soon as I get off screen, we're going to switch over to the other microphones. But until then,
yes,
we're going to switch things up just a little bit, because what I'd like to do is I'd like to go over a little bit about what we've learned in the industry.
Okay.
So normally we do this at the end, but because we have our special guest with us today,
it could burn a while.
Yeah, I'm gonna do this at the beginning because I told you actually just the other day, we have an update from Roku on their 4K Roku streaming devices, where they will be pushing out an update to give AirPlay 2 functionality on the Roku. And I did a little bit of research to find out exactly how that's going to work, and it turns out it's not what we thought. It is actually just straight up AirPlay 2 on the Roku device.
So it's full AirPlay.
Yep, full AirPlay. So you'll be able to stream audio directly from an iPad or an iPhone, a MacBook, or whatever it is.
So you no longer have to have an Apple TV in the system.
You no longer have to have an Apple TV. Now, so for everyone who is a Control 4 programmer, for everyone who does Savant or URC and uses the IP commands for Roku and understands what that means, where you can actually call up a specific streaming service, that's a huge, huge thing for that. So with that said...
Wait, we do have a little bit more news.
We do.
The Sony news I talked with you about the other day.
Oh, yes, yeah. Fill me in a little bit. Remind me again, please.
Sony is shipping their 8K televisions now. Mm-hmm. And they are a real 8K TV with a real HDMI 2.1 input.
Yes.
However, it is an HDMI 2.1 input, not a 2.0 or a 1.4.
Right.
And we are very, very early into the feature set and parameter rollout of 2.1.
Yep.
What this means is do not plug your 4K source with Dolby Vision into this input, because the 2.1 chipset does not have the parameters for Dolby Vision put into it yet, because they're still waiting to know how to put the parameters in it.
Plus that input doesn't have the 2.0 chipset in it for it to switch back, or it may have it, but it's turned off.
No, it doesn't.
Oh, it doesn't even have it?
It doesn't even have it.
Okay, that's
so you need to think of when you're setting up your systems. Mm-hmm. Think about how it's going to be employed, and if it's not an 8K device that's a legitimate 2.1,
yep,
don't use that input.
Okay, there you go. Well, we've got some really good news for everybody then. So Roku is coming along. Leo, good to see you. The experts, good to see you as always. And Leo says, #kill Apple TVs. Yes, as much as possible.
Well, and by the way, the header for the Roku press release was HBO Max.
Oh, that's what it was. Yes.
Right, because you get that on the Apple TV.
Yep. So, and that's the other thing, that I guess they're bringing HBO Max to Roku then.
Oh, but that's through your streaming device, your handheld device, your media, not through the Roku, but through your handheld device.
I will say I'm putting a lot of faith into Roku as a company as a whole. So if Roku decides for some reason to change something and make it to where we are not able to have Roku control on something like Control 4 or whatnot, I'm going to have some very upset customers. But that's another thing entirely. So disable the one click so that the device doesn't wake up your devices. Leo, fill me in a little bit more on that. What do you mean by that? Disable the one click so that the device doesn't wake up your devices.
Does that mean that the one click will turn on the TV?
Maybe.
Because if it's waking up your devices, I assume it refers to everything downstream, the AVR and the display.
Leo, elaborate for us real quick. Okay, so Brent, today's episode, of course, we have a special guest, like we said before. And at this point in time, I'd like to go ahead and bring him on, and I will step away if that's okay. So as always, if you guys have any questions or about anything we have going on today, definitely leave it down in the chat section, or if you're watching this after the fact, leave it down in the comment section below. Brent, we are up to 984 subscribers. We are 16 subscribers away.
Please subscribe.
Yep. Hit that subscribe
I would
button,
get on my
notification.
knees and beg, but you won't be able to see me, so...
Yeah. So with that, everybody, thank you again who has subscribed. Definitely share it out to everybody else so they can know what's going on.
And don't forget Facebook, Instagram, Twitter.
Yep.
Pinterest? I don't know.
Well, Pinterest, sure. I guess. I mean, it's not really a thing, but yeah. I don't think we have a TikTok yet. Maybe we should get a TikTok.
Just before it gets banned?
Just before it gets banned, yeah.
We'll along with our WeChat?
Yeah, exactly. So, all right, everybody, I'm going to step to the side, and I'm going to bring on Mr. Jeff Boccaccio onto the scene here.
And switch over to real audio.
And I'm going to switch over to real audio. Jeff, and I'm going to get my mask.
There you are, sir. Hey, Brent.
Hello, Jeff.
What's going on, man?
Oh, yeah.
Absolutely,
now-
absolutely.
Since you can see
So-
yourself, make sure to stay in frame.
Yep, I've got it.
So
I've got it.
before we get deep into this, there's possibly somebody out there, possibly,
Yeah.
that doesn't know you. So
Oh.
tell us who you are,
okay.
what you do, and
Great.
with who.
All right. DPL Laboratories. It's a test and measurements company. We started about 10 years ago, primarily because HDMI was such a problem and interoperability issues are so high. At the time, we were also a contract engineering company. Of course, we got all the bad news too, just like all the installers did, as the hardware that we made was also running into issues. And we finally decided we would have to do something about it. And we owed that to our clients, as Metra was one of our clients, and you know, they're in trouble. We got to help them out. And so what we did is we instituted a very intense case study program around the world. I mean, whether it was in here at Metra or whether it was in the field or in our laboratories, we looked to see why these products were failing. Literally taking these case studies, and it took about 2 or 3 years of research. Spent a lot of money, did a lot of traveling, and we discovered that the way the products are tested, they're good. I mean, it's a good test a good test parameter. The problem was that there are so many variables between all of the products that are being made. It wasn't necessarily a component problem. It was more of a system environment problem, and the test program that they use isn't really made for that. And so we designed our own test program, and with that test program, launched us into an area where, you know, a lot of people just say, geez, can you test mine? Can you test mine? And we finally started DPL Laboratories.
Well, and that's great for DPL, but who are you?
Oh, I'm just Jeff Boccaccio. I just come up with some ideas and.
Now, how long have you been in our industry?
Oh, too long, Brent. Let's see. Since I'm older than you, longer than you, I started in the Macintosh area when I was 16 years old. So
By the way, that's Mac Audio, not
Mac
laptops.
Audio, yes, of course. And I was 16, so. Let's see.
1948, 49?
No, no. What do you mean, 1949 for when I was born?
16.
No, it was probably in the early 70s. Early 70s when I started. Yeah.
So you got me beat by 5 or 6 years.
Yeah. Oh, yeah. Yeah. You know, I had a great opportunity, and it was fun. And now we've both built up to higher levels, right? And especially, you know, when you're in the test and measurements business, you're dealing with technology that you know no manufacturer gets to see. And in fact, we're going to talk about that today as we talk about 2.1, on what's going on, where it's going to go, how you're going to manage it, and some of the precautions that have to be taken from a manufacturer to make sure that they get the products that they're going to work. So we can move into that.
Okay, now, I did see that you brought a PowerPoint with you,
Yes.
and which you were famous for.
Just a few
So
slides.
we're going to get into that, and luckily for us, Adam is off camera running the video switching today, because it will be a little bit more intense than what we typically do, and controlling the PowerPoint, hopefully keeping up with Jeff's demands. So tell us a little bit about what we're going to be seeing in your presentation, sir.
Okay, well, first off is the first slide is about our announcement of 48G. This new testing program has been 2 years in the making. All new test equipment, all new test procedures, and we've escalated the level of test into much higher data rates than even what HDMI calls for, and we've also, of course, instituted our past technologies in history on what happened in the earlier days with HDMI, which is still basically the same thing and under 2.1.
Well, now, wait a second. I want to step back a second. You say you're looking at a higher bandwidth than HDMI requires.
Yeah.
I have to know, why are you doing this?
It's like, you know, it's kind of like if you want a car and you want to drive that car at 60 miles an hour, you know? So what do? Buy a car that can go 60 miles an hour? You can do that. You won't get any performance out of it. But if you want to really get performance on it, you know, get one that can do 120 miles an hour. That's what I'm talking about. Headroom, speed, accuracy, okay, visibility. It'll blow your mind what we have now. And We can do test and measurement now that is unbelievable. The difference with the new spec is that the bandwidth is so big, not being that it's out to 48, but that we have to really concern ourselves with backwards compatibility, which means we have to go all the way back down to 3 gigs. So it's a very large bandwidth to take care of, and it's like anything else. The wider the bandwidth, now the transmission line has got to be somewhat linear, which it never is, but somewhat linear for this whole dynamic bandwidth. And how do you get there? And we're going to show you that today. It's going to be amazing to see what happens.
Are you ready for the next slide?
Let's go for the next slide. So we're dealing with data fidelity. And, you know, a lot of people don't understand that. Data fidelity is what kind of distortions that you would see in raw data. It's kind of like, again, back to, say, stereo amplifiers. You can get stereo amplifiers that can work from 20 to 20 kilohertz, that may be 100 watts per channel, but they may be doing 1% distortion. And then other products can come in that'll operate at a 0.5% distortion. And of course, the lower the distortion, the better the definition, the better the understanding. It's almost the same thing with data. It also has a sense of distortion. Only its distortion is multifaceted because it doesn't happen in one instance. It happens in many instances throughout the size of the data that you're actually producing. And we do these measurements for any high-speed data. We do them typically with both frequency domain platforms and time domain platforms. And you know, we'll get a little bit more into this as far as the differences between the two. But you know, you really should be doing both if you're gonna really play in the big league. And you know, there's a lot of people that don't. There's a few people out there that are still supporting both frequency and time domain. But you've got to know what you're doing. If you know what you're doing, they're going to be having to use both. And so let's go to the next slide and see what that is. Now here's a perfect example of data fidelity. So on the left-hand side, we've got a perfectly good square wave, and that square wave is nice, clean. But you see the up pulse or the rise time of that is one pulse. It's one excitement. It's one event. But what makes up that whole entire square wave are many events that make up that whole square wave. But if you ever looked at a sine wave in audio, it's one event. That's all we're looking at, is one event. But in square wave, you know, you can't be. You have to be looking at many events in order to judge how the square is reproducing the actual data that we're trying to move out. On the right-hand side, this is an example of what a distorted data bit would look like, and that's typical. You know, it goes down a wire and goes through some degeneration, and then it comes out like this. Some are worse than others, but in order to see what those are, you have to look at them more in the time domain. If you look at them in the frequency domain, you basically look at maybe what the frequency response is, but only for one instance. You can't do it over time. Okay, let's go on. So just to give things a little bit more perspective, on this screen you see on the left-hand side we have this is a network analyzer, and what it's doing basically is showing us the insertion loss of this particular product. Or if people don't know what insertion loss means, it's primarily frequency response. So if you look at that graph, you can see that the response curve starts relatively good on the left-hand side, low frequency, and it begins to pitter off a little bit on the right-hand side. But now you go over and look at the I pattern, which is time domain, and you can see it's clean, robust, and there's a nice big green pass on there. Yes?
I have a quick question.
Yeah.
What causes the petering in the frequency response?
Well, a lot has to do with that. Most of it is capacitance.
Okay.
There's capacitive loading in there. It's inductive loading. There's resistance in there. So you have to take every resistor, every inductor, and every capacitor, and they work series parallel.
So it's aggregate failures.
So it's aggregate failure. It just eventually will pitter out to nothing.
Gets tired and gives up.
Which is why that with 48G, you know, we're lucky to see copper get to 5 meters. I mean, that's a dream, right? And you know, we're beginning to see some of those come in, but that's all we're going to see, and we're going to show you why in a minute. So, and so this last slide shows you that the characteristic of the eye is so important because it tells a story. Let's move to the next and I'll show you what that story looks like. So this is a perfect example of what a story looks like. See, in an eye pattern, we get all kinds of data. We get amplitude data. We got rise time data, IMAS data. We have jitter, which we can't get. We have histograms, that little blue upside down mountain. That means a lot because that tells us about noise, and it also tells us that we're getting a nice smooth Gershon type of noise level, which is what we really want. Sometimes you'll see those histograms come in where there's actually two histograms, where it's multi-moded in that, which is more distortion during the changeover from high to low. So the whole idea is to try to keep that crossover notch that you see there just below the upside down blue mountain, and keep that as thin as possible. And by doing that, you'll get low jitter and a very well-defined eye. So there's a lot here to look at. And when products come into DPL Laboratories, we don't just wait for it to pass and fail, which the equipment's very automated, it'll do that. But what we do is we try to analyze the waveforms as the products come in, because every client that DPL has, we don't just hand them over a paper, we brief them, we have a meeting with them. And Brent, we go through these meetings all the time. And Brent has learned through these meetings what an eye should look like, what can we do that's better. So sometimes they'll pass, and some companies, and Metra's one of them, they'll say, well, that's really good, but I noticed over here, Jeff, right? I got a little noise over here that Brent learned, right? Can we make that better? Right? What can we do
I don't want failures. I don't want the phone calls.
Exactly. And the further you are up, of course, the less amount you're going to get for failures. So there are a lot of companies that are proactive with this, and there are a lot of companies. All right, let's go to the next slide.
Wait, can I step back a second and explain jitter in the HDMI signal?
Okay, jitter is, I got a good slide for that I didn't put up. Boy, that's too bad. Basically, it's this. If we went and looked at that square wave we had earlier, that one square wave, can we go back to that one real quick? There you go. If you look at that left-hand square wave, and you see how nice and clean that is, there's no jitter there at all. Just look at the vertical
right.
rise and the fall, right?
Defined, very defined.
Very defined, right. So now, let's say that we were going to do that over time. Remember I told you, time domain. So over time, we may have to generate 48 gigabits, right? And the faster you go, the more chances of more mistakes happening amongst the transmission. Well, what happens is that as the next one comes along, it may not be in the exact same spot as the first one.
Okay.
And they keep moving back and forth. And
so it's kind of like a slightly out of phase echo?
It's not it could be used maybe like an out of phase, but it's more timing. So it's like this is happening if you're waiting to bring it down to microseconds, you may have one at 10 microseconds, another one at 11.
So they look the same until you get in a very defined scope.
Yeah, all of a sudden you get when you get to these really super scopes, now you can look at these in picoseconds apart, and you can see this jitter just build. And the closer that thing gets to the middle, the more the chances of error.
Okay.
Good question, though, Brent. All right, let's move on to the next one after this. Okay, this is good. Here's another example of time domain versus frequency domain. On the left-hand side, we have, again, our curve, which is, almost perfect. I mean, it looks damn good. A little breach in the lower end, but look at the eye pattern. It's a disaster. And it's because you'd never see this in frequency domain. You have to look at it in time domain. So any manufacturer that has any brains is going to look at this and say, geez, I want to make sure I see my time domain numbers, because that tells the story about that particular product. Okay?
Oh, now, is the time domain is a little bit unique to what DPL is doing?
No. DPL does that at a much higher speed, yes. But anybody in the high-speed business, anybody, if they've got any professionalism, they do both. Now, most of them will fall back into frequency domain. Frequency domain came out as parameters. Early 60s. I mean, it's been around a long time. Hewlett-Packard did it in the 60s. And time domain didn't come out, of course, when we started getting more and more digital technologies. And we had to look at these things. And back then, fast was a gig, right? So what happened? We started off at 5 gigs or 1.65 gigs per channel during the early 2.0 days. And then we kept going up and up and up. And now we got the 6 gigs per channel under RIF 2.0. And now we've changed over to FLR, and it'll take us out to 12 gigs per channel. So as we go up in frequency, this thing gets more and more critical, and you need faster and faster equipment to look at it. Okay, let's move on to the next slide. Yeah, so here you go. This is what we've been dealing with. This is it. This is current stuff.
And we're just kind of getting there now.
Yeah, we're finally getting our hands around this thing, and 18 gigabits was a big envelope for us. We had to really search to make sure we even got that right, and we did. We got some good test equipment to do that with. But you see how big this is. It's 18 gigs wide. But you see the interface, in this case, was only 18 gigs. That's all we had to deal with. We only have to deal with 18 gigs. And when you drop down below that...
I like the way you say only 18 gigs when 4 years ago the concept of 18 gigs was, oh my God.
Unbelievable, right?
We got to deal with 18 gigs?
Exactly. So, 18 gigs is actually pretty easy today. And the reason why I say that is because within that 18 gig envelope that you see there, you still have 1.4, which is operating at 10.2, and you still have 1.3 operating at 10.2. And then, of course, you go drop down into HDMI 1, which is operating at 1.65. So those lower numbers didn't require anything special. They were so low in frequency, life was easy then, very easy. But as we move up into 1.3, 1.4, we needed a little help, and we needed what's known as a equalizer or a...
Repeater?
No, I'm going to call it a correctional amplifier.
Ooh, a CA.
You like that one? A CA, yeah. We'll keep that one down. CA, we had the CA. So the correctional amplifiers are used everywhere. You use them in amplifiers for audio today. They're tilts and bass boost and trebles. They're basically correctional amplifiers. It's the same thing in digital, a little different in the way they're designed, but they basically do the same thing. So let's look at that kind of equalizer used for 18G. See, here we have 4 eye patterns in 18G. That's what we have to test for. And we have to look at it in increments of not only each test pattern, but again, we look at the eye, we look at the noise, we look at the jitter, we have to look at all those things. This equipment reports this instantaneous in text. And it also does it in images if you want it. And it does it fast. So, of course, at 18G, the equipment has no problem moving along with this, right? However, let's see what happens also under these tests. Let's go one more. What?
Before we go a lot further, as we have gone from 1.65 to 5 to 7.65 to 10.2 to 13.65 to 18, does the chart kind of move up? I mean, do you lose the ability to properly handle the lower frequencies in a lot of cases? Just because they're lower resolutions doesn't mean they're always handled correctly.
No, up until 18, it hasn't been that hard. We're still within 20 gigs of bandwidth. It wasn't that hard on the transmission line. I mean, the linearity of the line is important, and it's an excellent question, Brent, because there are some that we find. That. I mean, you've been in the lab, you've seen them, where some of them take these dipsy doozy curves.
It looks great at 18 and doesn't look so good at 13.65.
Yeah, we got them in. I mean, we had one product come in. It worked at 6 gigs. It wouldn't work at 3. So that doesn't. Sometimes the math doesn't work that way. So you really have to look at all of them to make sure that when you buy that cable, and no matter what it is, whether it's 3 gigs or 6 gigs or in aggregate 18 gigs, just make sure that it's good. That's going to work with everything the customer is going to have, including Apple TV. I happen to hear that, so I decided to. So let's move on to the next slide. Okay. So here is a perfect example of what happens under 48. Notice what's happened here. We still have our 18, but we've got in the yellow, a huge envelope to deal with other data rates that we have to be contending with because they're different feature sets. So now we have 24, we have 32, we have 40, and we have 48. And all of those have to be tested, and they've got to be tested again, especially now with time domain, so that we can see what these things look like at those incredible speeds. So in order to do this, this is what the new test looks like. Next one.
I think that's what the clip was about there, Adam.
There you go.
Right. This is what we have to do now. Notice, there is a hell of a lot of eye patterns being generated, and they're all being generated at different data rates. And all of those eye patterns have to be analyzed, not only for each data rate, but also channel by channel. And it takes time. I mean, even before we only did one, it took us, at best speeds, we're maybe doing it in an hour, right? Now look at this. Now that's an hour for each waveform. So, you know, for each cable test. So now we have to do all these cable tests, and of course, the longer it takes, the more it costs to test, which of course raises the price of the product. So we have
But it validates the product.
It does, but there are ways today with high speeds, right, that you can do this. The speed that we're operating at is 400. So it's 100 gigs per channel. We only need
Versus the 12.
versus the 12. Most products out there are going to be operating at 25.
Okay, so you've got a tremendous amount of headroom.
Huge amount of headroom.
But it also allows you to get a lot more detail at the lower resolutions.
Yeah, and we can zoom in on this thing and we can pick it apart. It's a fantastic machine to do this with. And it does it fast. Again, it snaps off the entire, it'll do the whole envelope of one data rate in about 7 seconds.
Jeff, now we don't have any questions yet from the chat, but I do have a question myself personally. On the 32 gig frame here, I just noticed that the fourth channel on that one.
Very good.
It looks like what's going on there? What's happening there?
Good catch.
If you'll,
I can't see it.
I was going to dump on you, Brent.
I can't. I don't have my glasses on. I can't see it.
I put that there just to see if maybe you'll spot it.
I can't
is
see.
that one of ours? Is that one
No,
of ours?
no. This is not one of yours. Actually, I am not going to say who this is.
No.
However, it was discovered. This is 12 gigs. These are 12 gig measurements. And notice that
I'm going to walk over there out of frame because I got to see what you guys are talking about.
you'll notice that it kind of almost looks doubled.
Yeah.
Yeah. Well, this particular cable, they sent in 5 samples, and all 5 samples had that same doubling.
Now, is that multipath?
No, it's phase.
What we talked about earlier.
Yeah. But you see, the phase gets a lot stronger, a lot harder when you get up to 12 gigs. This cable would never work. I mean, there's signal there, but it's...
So let me ask you a question, because this kind of takes us back to frequency versus time. If you just looked at a frequency sweep on this cable...
You'd never see it.
That's my question. So this would pass a frequency sweep.
Absolutely.
And you would get a product that passes the spec, but won't work.
Yeah, in fact, it probably passes it extremely well. I mean, I wish now I would have done the insertion loss curves, but if you saw the insertion loss curve in that thing, it would be really stellar.
So did you run a histogram on that one as well?
Well, we didn't have to. I mean, you know,
I get it, but this is something that I would love to see more detail of.
Yeah, we can.
Because this really comes down to, and thank you for catching that, Adam, because honestly, I just see green.
I was sitting here waiting. Someone going to say something here. So,
if kind of back to if it would pass the frequency, when this is scary. Because if all somebody does is a frequency test and gets the approval, they get it out in the field, it won't work, but it's still got a stamp on it from somebody.
That's right. You see, what you have to be careful of is that, remember, I told you all 5 samples did this. That means...
So that's a build issue.
It's a die lot issue. It means that whoever made that particular run of cable, it was like that through the whole thing. So one channel was off, in phase, and of course it was consistent throughout the whole cable length. So that product, in fact, I could tell you that, which I didn't do because I thought we didn't have enough time, really, but that particular product, it works perfectly fine at 6 gigs. If I ran it at 6, you see a perfect die. So a guy would very easily plug it into a 6 gig system and say, oh, this is great. That's what they did there, right at the factories. Right at the factories.
Oh, yeah.
That's all they use, a TV set. They plug it in, oh, yes, works. Well,
what he's saying is for factory testing where the cables are made, they'll have 1 or 2 sources, a couple of TVs on the line, and they just go, next.
I mean, talk about plug and pray. Holy crap. I mean, this is exactly what we're trying to prevent. And of course, as we move up to 48, these problems, we never saw these before. It didn't really happen.
I say, walking over there to get a good look, I've never seen that eye pattern from you in the past.
Yeah, it's new. It's new, and it did that all the way down to about 8. By the time we started losing it at 8, and then by 6 it cleaned up.
So you could plug your Apple TV in or your Blu-ray UHD player, and you're going to get a great picture, and life is good. Until you get to that new 8K source, and suddenly that cable that's supposedly certified ain't working.
Yeah, moving to FRL, and you're going to be in trouble. Okay.
On that note, are you going to cover FRL later in your discussion, or should we cover it now?
We can talk about it now.
Let's do that now so they understand what you're talking about.
All right. FRL is called fixed rate linking, and basically what they've done is In order to get it up to 48, how do you do that? You only had 3 channels to start with. So under FRL, they take off the clock channel. That's no longer there anymore. And they actually put another video channel on that. Now you can multiply the number by 4. And they take the clock and they embed the clock in the signal. So we don't have to worry about having the clock anymore.
So, right. So now all 4 channels are a red, green, blue clock. Instead of a red channel, a green channel, a blue channel, and a
I'm
clock
not sure
channel.
if they actually synchronize to a color, but they are definitely discrete in nature. And under TMDS, of course, we only had 3 channels.
Right.
And the modulation is a little different. The way they remember, it's transition modulation, right? So under FRL, it's not necessarily like that. So the ratios are different under FRL, which gives it better throughput, lower characteristics and emissions, and they have to be very worried about emissions when it starts getting up to this frequency response.
Yeah. Yeah.
We'll cover that at the very end.
Okay. Next slide.
Next slide, please.
Wow, I gotta hit the right button and make it over there.
All right. Now here's a perfect example of how there's correctional equalizer we were talking about earlier. Under 18G for the last, 10 years or so, since 2013, 2012, yeah. We've been operating under 6 gigs or 18 gigs.
Potentially.
Potentially, yes. Or 4K, whatever you want to call it. And the system required 1 equalization correction amplifier. It was inside the TV set. And every television set you put in, from 1.4 and on, mandatory to have that equalization. Actually, I'm sorry, 1.3 and on. Mandatory to have that equalization curve in there. Otherwise, the longer cables just wouldn't work. I mean, you wouldn't get out of your way at 3 meters. It just wouldn't work. And we're only talking, 3 gigs, right? But that's what it took to do that. So let me show you what the curve looks like on this particular equalizer. You see this curve here. Notice it's focused just after 3 gigs. So this is more toward the Nyquist side. And by way of just
And that's a 10 dB bump at 3.8 gig?
It's about a 10 dB bump and about 12 dB bump at for 6 gigs. It's about a 3 dB bump. I'm sorry, a 10 dB bump at 3 gigs. But the point is that's relatively easily to solve. And what do we measure for? Next slide, please. Is that little dot? Oh, too far. So that little dot is where we want to look at. We want to look at what the spectrum looks like that with an eye pattern. And if everything's right, especially with sin x over x, we talked about that a couple of years ago, and basically the harmonics of the waveform produces enough bandwidth and throughput for us to get up to 6 gigs with it. And it worked fine, yes.
And by the way, the discussion on sin x over x is one of our videos, which is on the Metro YouTube channel, so please take a look at it.
That's what the fans.
Yeah, that's where we actually sat down and did the interview.
Yeah, that was good. That was good. So that's what we have with 18 gigs. This is what you're dealing with now, but this is not what you're going to be dealing with when 48 gets going. Let's move on. So now in a 48G set, we don't have 1 equalizer anymore. Instead, and one more time. Instead, we have 8 equalizers.
Now, is that per channel or per?
That's 8 equalizers per channel.
So 32, really?
32 total, yes. Well, hell, I mean, think about that one for a minute, because now you've got to consider what's going to happen to the equalization curves on that, and where do you measure? What do you measure? We have different data rates. We already saw that, and the equalizers are going to have to be working inside those data rates, because the data rates span anywhere between 3 gigs and 12. So you've got to have, again, some form of linearity around this thing. And HDMI knew that, so they parked in all these equalizers. And these equalizers make it so that we can shape that any way we want to. I'm ready for the next one.
It's like looking fancy 16, 32 band EQ from the 70s for
Remember that?
Hi-Fi.
Yeah. Oh yeah, let me just pull those up, right.
Get those little dots lit up on your ADC equalizer.
Yeah, right. So this curve here is gonna, okay, he's ahead of me, it's okay.
Sorry about that.
This is the equalizers used for 48. A little bit different than what we had in Rev 2.0.
Yeah, the curve's a lot softer coming off the apex.
It's a little bit, so it doesn't have that major peak. It's relatively broad banded. It does have a uniqueness to it under 1 gig. And it does have different levels, as you can see, when you go from one equalizer to another one.
So each one of those is a different EQ curve.
Yes, and it's up to the television to decide which one you want to use.
So it will.
Can you imagine?
So the TV is going to interrogate the system and the cable and say, okay, I've got this capability.
Right.
Here's what I need. Here's
Correct.
the EQ. Well, that resolves one of the issues that we saw in the 2.0, which was it was possible to either overdrive
Exactly.
or underdrive a panel.
Exactly. That's right. But that still doesn't go away, Brent.
It doesn't.
No, I'll show you in a second.
Wait, what?
It doesn't go away. Let's see. No, hold on one second. So now what I'm going to do is I'm going to say, okay, Adam, what I want you to do is when I click the button, because you're now going to see all the spots now we have to check it at. Go ahead. So now we're looking at all of the markers, the marker points that are needed for us to examine and test that cable. We only had one before. Now we got 40. So we have 40 examinations on each channel per frequency.
Per frequency.
Per data rate. So you have to multiply that times 5. Right, so you got to have speed.
Okay, back up a second. We've got 8 individual EQ curves, a total of 40 points per channel per effective resolution.
Right. That's right. That's the right way to do it. That's the right way. Now, you know what's going to happen? You're going to get maybe some testing agencies that's going to say, you know, I can't do this. It's going to cost too much money, and it does. I mean, it's operator time costs money, and these things will get crazy in pricing. So, well, you know, I'll just do it at 12.
Okay.
Who'd ever know? Except for the guy that wants to use it at 10 or 8 and finds out he can't get 8. Especially for those guys that are counting on 8K, aren't they? So, you know,
yeah, yes, they are, and products are going to be shipping soon.
We're gonna have to start thinking ahead now, guys, because you got to start thinking about the infrastructure. You got to start thinking about the long distance cables. And oh, by the way, there's no testing for active cables except for moi. We have it.
Oh,
of course.
Yeah, of course.
Of course.
One of the things that Adam and I have talked about is looking at TVs. Most of the sets that are out there now are really only 40 gig sets. They're not 48 gig.
Oh, really?
So, and
We're
I
in
noticed
trouble.
the way the curves are looking, you guys do 40 and 48 independent.
Yeah, we do everything. We do it right. Every single dot up there we check out, and you know we have to be vigilant on making sure that not only are all the eye patterns looked at to the data rates you saw earlier, but we have to check every single equalizer. And I'll tell you why we do that. It's because let's say that we had a 3-meter 48G cable.
Okay.
And let's say that cable comes by and, you know, works pretty damn good at, say, 3 dB. Remember, we have 1 to 8, right? So it works pretty good at 3. All right, that's good. What does it do at 4? So you run it at 4 and you find, hey, it looks pretty good at 4. Well, what does it do at 5? Well, it changes because now it may have a good inner eye, but the outer eye will go into saturation. That's what I was talking about earlier. So now the machine's got, you know, think about, okay, I got to make sure I get number 3. Number 3 is my guy. I got to make sure I stay at number 3, right? So now we have to basically rely on the television to drop us into a 1 dB increment. And Brent, that's dangerous. You know, we have to have some dynamics there. So we have to look at all of them, and we have to see if what is the whole dynamic range, what does the picture look like? And then how do we improve it if we have to? And as time goes on, we're gonna learn more and more about their improvements. But this is a perfect example of the complexity of how important it is and how this test process
But this
goes.
does allow a little bit more flexibility in the installations in the past, because as long as something's working in each channel, you should get a picture.
Well, then we'll talk about that as we move into link training.
Ah.
Is that next? Can't remember now. It is next, yes. Okay, so now that you've learned all about equalizers, you learned all about data rates, you know all about time domain versus frequency domain, you understand what the anatomy of an eye is and how to read it if you want to. And if you want more help with that, you know, get a hold of Metro, they'll help you, or clearly DPL Direct, we'll do it for you. We'll help you. We want you to succeed. This is our mission, is for you guys to have 0 problems in the field as best we can. And whatever we can do to help you do that, we're there. But when it comes down to what we had in the past, Brent, okay? We didn't have those adaptable equalizers, did we?
No,
That's going to help.
it'd burn us.
Yeah, they would burn
everybody.
Us. Yeah, right. They would burn us, and they could still burn us today if it's not controlled, right?
And one of the reasons we had you with the GA2 to build the adaptive EQs into that,
that's right,
was because there were TVs that you could be too hot into on the same cable that were not hot enough on another TV.
Yeah, yeah, and you got to think about the fact that we still have to be concerned about what happens with actives, and we now have that. So after 5 meters or so, you're going to go active. A lot of it will be fiber. And then we've got another set of rules we got to walk through, because now the power supply is going to get that much more critical. And we've been hounding on people. You know that, Brent. Get the power, because the amount of power on the bus is so small. And HDMI needs that power. And, they failed us. In my opinion, the forum has failed everyone in not allowing the power to increase. It's only at, 50 milliamps. That's 0.05.
Now, do you think that's an economic decision because it allows them to keep the power supplies tiny?
I don't know, Brent, anymore. Why would they not do this? I mean, up it up to 100 mils. 100 mils, shit, that'd be great. We can get that stuff done. But they didn't do it, and so now the guys in the field are going to have to go back into external supplies, or they're going to be operating on levels of power that you could be starving the system with. Right.
Yeah, we know about that when we've killed outputs on matrices, on active cables.
Yeah, it's amazing. You don't know what you're doing, what you're playing with on this thing. You've got to supply the current, and there are some cables out there that we're seeing that are absolutely spectacular, but then again, they don't take care of the information channel.
It's a balance of everything.
We're talking about, it's an information channel where it sends data. We've talked about this 1,000 times. It's called the DDC channel. For $2, the cable can be repaired.
So, tell us about link training, because you're just about to go off into
what?
A DDC rant. I can tell.
No, I'm not going to go there. I'm not going to go there. No, I'm not going to go there.
So let's talk about link training, because I can feel it.
No, I'm not going to go there. No, it wasn't in the plan. So with link training, so what happens is HDMI basically, borrowed this from DisplayPort, and it's a good idea. It's a really good idea. There's a little bit of a gotcha on this. Let me explain to you what you're going to be walking into. You're going to have a customer. He's going to say to you, I want to have 8K. I want to have 48G. I want to have everything. I want it to works. So you go out there and you buy your LG. You buy your metric cable. You buy your source material, and you're ready to rip. Right? You turn the set on, and if it was an inferior cable, let's say not a metric cable, that's DPL Laboratories, but a cable that maybe didn't get checked like we just showed you, well, that cable could come by and say, I'm trying the best I can. The display will look at that signal and make a determination. It'll first go through all the equalizations. If it doesn't make it through the equalizations, then when it says, okay, and it does this all the way down to TMDS. So it'll go all the way down to the old 2.0 system. That's how far it'll go. So your customer could be looking at 18G at the end of the day. And God forbid...
Or lower.
And God forbid if the televisions don't come in with, on-screen displays that show the customer, oh, by the way, you're only operating at 18G. I wouldn't want to have to take care of that phone call.
No, and by the way, for the old guys, this is like looking at the auto baud rate for serial cables, where it would start up and work its way down to the baud rate that worked for that cable.
Exactly.
It's exactly the same thing.
Exactly, and it's great to think about it. Think about it, because now you say, oh wow, I could go in there and it just keeps going down. So if it goes out and says not good enough, it calls back to the source and says drop it another one. So it goes from 48 to 10. I'm sorry, 48 to 40. Drop it another one. Then it goes from 40 to 32. Drop it another one, and it keeps doing that all the way down into TMDS until it starts working. And if that doesn't do it, that cable's really got to be bad.
How bad is it, Jeff?
I mean, really, right? I mean, you're talking about getting down to 1.3 stuff. So you've got to be concerned about one thing. It may save your butt. Don't get me wrong. You walk out of there, the customer sees a picture, and you got your money in your hand, and you're happy than a clam.
Yeah, I could see it being a big plus for the retail market. but
Yeah.
not that, but not so much for the
custom guys.
CI. Yeah.
Oh, the CI guys, because you guys are smart. You guys know what you're doing. They look up to you, and we hear it all the time. We get phone calls all day long about people just bragging about their custom installation system and who did it. And you know, it's good because they're smart about it. But hear me out on this. Link training can really save your butt. But should they find out that they paid for something that they didn't get, you better be ready to respond. Because I've been in retail years ago, and let me tell you, these customers, they may be the nicest people in the world, but all of a sudden, they'll just turn on you. And
So-
you know, go ahead.
Yeah, the link training itself, that's between the source and the display.
Yes.
Now, is it the display calling back to the source in this
Yes.
case?
The display is the brains. So the source sends down, say, they do their EDID, and they say, oh yeah, you do 48? Cool, I do 48. Okay, let's go. 48. Then HDCP comes in, everybody's happy, right? Okay. Then it sits there and says, you know, that channel 2, a little dodgy there at 48, you know, why don't you drop it down one? So it sends a little code back up through the communication channel we just talked about. Not going to talk about DTC. So we're going to take that communication channel, we're going to bring it back up there, and it's going to go to the source, and the source is going to say, knock it down one set, boys.
Now, when you say knock it down one set, are we now looking at each channel independent? So if
That's
two's a
all
little
four.
weak?
No, it does all four.
Okay.
It doesn't, no, it's not that good. So it drops it down all four, yeah. And they go down and they say, okay, now it's at
So
40.
we'll start at 12, then we'll go to 10, then we'll go to 8, then we'll go to 6, then we go to 3,
and we're out.
and then have a nice day. Go
Yeah,
home.
you're out of business. And you know, one of them will work, and it'll save you. It will save you. Just be careful. You're best off. Run the system up if it's going to do this at the shop, and look at that display and make sure you're getting 48. I mean, you want to get the right product for sure, and products that are, you can see what we go through just to make sure you get that throughput. And I mean, you pass these eyes, and everything is really cool. So, okay, we're going to be tight on time. Let's run into emissions real quick. And emissions is another big one that you've got to watch for here, because as we get these large data rates, you know, the radiated emissions coming off any device, whether it be cable or even fiber. In fact, we have found that even fiber could be worse than cable.
Okay, you got me on this one. Explain that.
Well, you have to remember the wavelength. Think about the wavelength. So you think about back in the days of FM that we used to have, right? Remember the
Yes.
Yagi we had? It was about, 50 some odd inches wide. That was a quarter wave. So it's a big wavelength, right? So of course, the higher in frequency you go, the wavelength gets smaller. So we went to VHF, got smaller, get to UHF, got smaller. Well, that was only in the 50, 60 megahertz range. Right now we're into the gig range, and we went from 6. We went from 1.65 to 3, and then to 6, and it started getting a little dodgy. A little radiated emissions comes out, and now we're going to go to 12. And they actually added a little bit more to this because they use this new type of standard called CISPR 32, which is what you see in front of you here, and you see the parentheses there. That's what it's got to watch for. It's looking for anything being emitted within that spectrum.
Well, I'm kind of back to my fiber question.
I'll get to it.
Okay.
So this is emitting, and it's got to emit it to a level that's got to be tested by an authorized, emissions guy. So that's something very critical. And then what I wanted to say was, and so you got to be careful because it can interfere with Wi-Fi, cell phones, and it'll interfere with itself, so it'll cause intermittence. And it's a hidden ghost. It's a hidden enemy. You got to be careful what you're going to do. Now let me just cover
Before
this.
Before we get to fiber, does this mean we need to have more shielding in a traditional copper cable?
They do. They generally do not necessarily more, but better.
Okay.
Wrapping it the right way. Let me do real quick with fiber. So wavelength, right? That wavelength gets smaller and smaller and smaller. That's what they call them in nanometers, right? Nanoweber. So we're getting smaller, 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 smaller. When we get up there at 12 gigs, it's teeny. Mm-hmm. Well, the traces inside those shells.
Okay, so is it
really
the head shells, not the fiber
The
portion?
head shells radiate
Okay.
because they've got gain.
Right.
And they're radiating, and they can be worse.
Yeah, well, it's basically a transmit-receive set.
Oh, yeah,
so
you gotta go to one of these chambers. You go to these chambers, they've got this 10-meter chamber. They put the wire down there. Then they go about 10 meters away, and they got this big parabolic antenna, and they just take the thing and beam it right into it. And if it doesn't make it, you're out.
Adam had a question.
So we actually have a question from the experts. Brent, you may need to repeat this back to them because I don't know if they can hear me or not. They're asking, are we going to have a tester available to make sure the cable is passing 8K on the job site through the matrix and possibly the AVR?
The question is, will there be a tester for 8K 48 gig testing? I can tell you honestly, it's not going to be from us because we are not a test and measurements product manufacturer. I would recommend that to Meridio. That would be a question for them. I think they're working on an 8K generator, but that's their business, not ours.
Yeah. Well, demand.
We are a connectivity company.
Yeah.
We want to get you from there to there reliably every time.
I think demand's going to force it. Somebody,
somebody,
whether it's Meridio or anybody else, I think demand's going to force it because
So,
you're going to
probably
need
yes.
it. You're going to need it, or at least make sure you've got the product. Make sure it's DPL approved. Make sure it goes through all what we showed you today. You stay on course with that, you'll make it. And I think that's about it.
Now, DPL website, what is your address?
So www.dpllabs.org, .com. We used to be an org. And you can get on there anytime. The website's being changed over now. We're just in the middle of changing that over into the new 48G reference standard, which is now going to be the new system. And we will be checking cables all the way down to 3 gigs. So it's not like we're only going to do 48. But, yes.
One more question, I'm sorry. Leo is asking, if DisplayPort is able to handle larger amounts of data, then why are they not being introduced into panels and AVRs just like HDMI was when it first rolled out?
The question from Leo is plain and simply, why is DisplayPort, which in theory can handle greater amounts of data, not replacing HDMI is the short of the question.
And the short of the question is HDMI won them. I mean, DisplayPort's a great interface. It really is. It's already got embedded clocks, and they were way ahead of the game.
And HDMI had to run to keep up.
And you know, HDMI was at the right place at the right time, and they got loaded up with inputs, and you know, we test DisplayPort.
Does it also have to come down to the distance? Because HDMI
Sure.
is designed to going a little bit further than what DisplayPort is used
Well,
for.
DisplayPort can go the distance.
No, it's the same thing.
The cables are there.
Oh,
it's
they're
just,
identical.
They just haven't been that many
Yeah.
because there's not as many DisplayPort products.
Yeah, the data throughput on DisplayPort is almost identical.
Remember,
to
they claimed
HDMI.
MHL was going to get there, and that kind of just went.
Yeah. Good question, though, Leo. Good one, Leo.
There you go.
I like it.
Anything else, Adam?
No, I think that's it on this end. I don't have any other questions. If anybody else has anything, of course.
We have been running substantially longer than usual,
Well,
although it
you
did
know,
not feel like it.
We
Thank
had
you.
a good time, though, didn't we,
Thank you,
Brett?
sir.
I hope all of you had a great time.
For what it's worth, I'm Brent McCall with Metro Electronics Home Theater. Who are you?
Jeff Boccaccio, president of DPL Laboratories.
Any
And,
questions, you can come to call Adam or myself at the numbers listed.
Yep.
And Jeff, what is the number to reach you?
Oh, that's 386-615-2423.
386-615-2423.
Yep.
There you go.
Have a great day. Thanks for joining us.
Bye-bye.